and share with you the results. So it's a good split between the competition to constantly develop new control algorithms and increasing costs and complexity of software maintenance and support for multiple device configurations. So we will definitely be addressing these questions today. And I'd like to start by presenting to you today's panelists and introducing them. So today we have Ved Acharya joining us from PowerSys. He is the operations manager over there. Would you like to introduce yourself, Ved?
Yes, thank you, Boris. Hello, guys. Hello, all of you. I'm Ved Acharya. As Boris was mentioning, I take care of the technical operations at PowerSys. Yes, pretty much as Boris was mentioning, PowerSys is a company where we distribute a software for electrification. We also provide services, and we do cover a spectrum of electromagnetics to power electronics to power systems to system level simulations. Perfect. So looking forward for this presentation, and hope you all have a good time. Back to Boris.
Thank you very much for that, Ved, and it's a pleasure to have you joining us today. Next, I'd like to introduce Peter Gartner, who's our senior modeling team engineer at Typhoon HIL. Peter, would you like to introduce yourself?
Yeah, sure. Thank you, Boris. So, hi everyone. My name is Peter. As you can see, I'm a modeling engineer here in Typhoon HIL. So, the main things I work on are basically algorithms for simulating machine models in real time, also the converter models and circuit solvers. And I would keep it short here, and then we can have more time for the demos and everything. So thanks again. Hope you have a good time.
Thank you very much, Peter. And my name is Boris, and I will be your host today. So just quickly to go over what our agenda is for today. We've covered the introductions. We will go and present to you the solution overview of the JMAG Typhoon HIL. Then we will move into the demo section in which we will show a couple of demos starting from the JMAG designer through JMAG-RT and finally use in the Typhoon HIL environment. And we will have a questions and answer section at the end of the webinar. So we look forward to answering any of your questions that you might have during the webinar. And with that, I'd like to transfer the screen over to Ved so that we can get into the presentation. So Ved, if you wouldn't mind, would you like to tell us some about the motivation behind this partnership between PowerSys and Typhoon HIL?
Absolutely, Boris. Let me share my screen real quick here. All right, Boris, if you can confirm if you can see my screen.
Yes, I can. Perfect.
Perfect. Thank you. Thank you, Boris. Thank you for the introduction, and hello again, all of you. So as Boris was mentioning, I would like to begin with shedding some light on the motivation for this presentation, or rather motivation for this solution that we are going to be presenting today. So looking at the increasing EV and HEV propulsion and the markets for EV and HEV, we also understand that there is an increasing control design and test requirements. So that is one of the motivation that is highly moving forward for us to present the solution. Also, there is a need for streamlining the development process. Basically, this can be addressed by model-based design and testing practices. In general, with use of MBD and testing practices, we have seen that 30% of improved schedule performance, and there is a 70% reduction in the number of defects, and then 40% more control code can be produced. Also, there is always definitely a need for eliminating the inefficiencies. And today we see lack of integration between design and testing tools creates a lot of inefficiencies. To address most of the part, PowerSys, JMAG, which is our software tool, and Typhoon HIL have come together to provide an integrated design and test solution tailored basically for automotive and motor drive-in designers. Taking a little bit further and basically looking at the V cycle, which is the development cycle of EV motor drives, we can achieve reliable design right from the initial stages. So there are two phases again, design and testing phase, wherein the combination test can be started as early as right after motor design. Basically, to be more specific, what we can do is we can test machine and control together at an early stage by integrating high fidelity models. This way, what we can achieve is we can attain shorter and faster drive cycles or development cycles. So with this, what we are going to present today is a solution which is a better way to design and test motor drive control. So what we are presenting here is a solution which involves JMAG and Typhoon HIL integration. So we are going to cover something about JMAG, how you create these high fidelity models, as you can see on my screen. Just to give you a framework, the screen shows how an FEM model can be converted to a lookup table based model, and then how we can integrate that with Typhoon HIL solution to better provide an integrated solution for this for achieving all the motivation points I have covered. All right, moving on to the next slide. Starting with JMAG-RT. So what we'll do here is we will just go a little bit brief introduction and set the pace for the next talk and also the demonstration. So we'll quickly look at what JMAG-RT is. JMAG-RT is basically a tool that generates high fidelity plant models for system level simulation and real-time simulation. Now, when I say high fidelity model, it basically captures the comprehensive motor characteristics that can be extracted from an FEA model. To be more specific, we can take into account nonlinear effects, saturation effects, and space harmonics. Now, this JMAG-RT is used to develop this 1D model, which is basically a lookup table that can be used in hardware-in-the-loop simulations, which can connect a physical ECU to a virtual motor. All right, how do we model JMAG-RT, or how do we create a JMAG-RT model? There are different ways of creating it. As you can see on my screen, there are different tool chains. So there are, as the blocks show, there are 4 ways of creating the JMAG-RT model or the lookup table. First one is to model it from JMAG Express. JMAG Express is basically a template-based tool wherein you input certain parameters of a motor and then you can output the FEA results from that template-based design tool. Then you have JMAG Designer, which is a full-fledged FEA electromagnetic FEA analysis tool from which you can generate a JMAG-RT model. You can also, if you have your test data or measurement data, you can also input a CSV file to basically develop this lookup table. And also on our website, we do have commonly used motor models, which is called as motor model library. You can download it from there as well. Now, the JMAG-RT modeling workflow involves us first to create a FEM model with JMAG. The second stage, we start JMAG-RT library manager. Of course, I'm just talking about the workflow and the framework, but later we will also go over the demonstration. And in the JMAG-RT library manager, we basically import the FEM model, and then we specify some of the settings that are required there, basically give some current angle and current amplitude inputs. And then once we run this RT model, it outputs something called as RTT file that can be further transferred to Typhoon HIL Control Center. Now, from here, I will pass it on to my friend Peter here, and he will take it over and talk what is it that he's going to do with this RTT file or the high fidelity plan lookup table that I'm providing it to Typhoon.
Okay, thank you, Led. Let me just quickly share my screen. So, just a second. Okay, so Boris, please let me know if you see the slide now.
Yep, everything is perfect.
Okay, great, thank you. So from here, what we want to enable to the users is to seamlessly import the JMAG-RT generated models into Typhoon Hardware-in-the-Loop simulators. So the idea is that for the user just to take the RT file, load it into the model, and be done with it, basically without any further modifications to the RT file. So the machine models that are described by the RT files can be simulated in Typhoon control hardware in the loop applications. And along with the detailed motor model, the Typhoon simulator also covers the rest of the power stage. So converters, transformers, batteries, and whatever there is in your system. So that leaves us with a completely virtualized power stage, and to which we can connect an actual controller. And so the controller interacts with the emulator, but it doesn't actually know that it's connected to a virtual power stage instead of a real one. And what we see as the key advantages of this control hardware in the loop approach, and first compared to some other approaches like model or software in the loop, is that we can actually test the controller as it is. So the same controller, the same control hardware, the same control software, the same firmware that is going to be used in the real system is just connected to the hardware in the loop simulator through analog and digital outputs, inputs and outputs, and if necessary, communication protocols. Then this allows us to test our controller in real time. So basically, again, compared to, for example, software in the loop, that would typically be an offline simulation, which could take a long time to simulate, for example, 1 second of the system behavior. With the nature of the controller hardware in the loop, we don't have that luxury, and we actually have to have our model running in real time. So 1 second of the actual behavior of the system must be simulated in 1 second. Next, compared to lab testing, conventional power lab, we have a much higher test coverage available with controller hardware in the loop. So we don't need to be concerned about breaking any equipment. We can also test some critical conditions like faults and basically any operating conditions that are unsafe for the equipment in the power lab. And what's nice about this is that we can also run pre-made batches of tests every time we make a new change to the controller, and we can basically be safe when moving on to the real prototype. So any changes made can be tested right away on the simulator, and if we missed anything, we can go back to debugging and so on. And from the project schedule point of view, we can start testing the controller without the actual power stage prototype, and we can completely automate the testing process. So I'll just quickly give a quick overview of the Typhoon HIL emulators. So basically they are built for power electronics drives and testing, and they use very application specific processors. So it's been on the market for more than 10 years now, and it's continuously improved and expanded upon. So it really focuses on power electronics and power system applications. The FPGA solver that solves the circuit can run with the simulation time steps of as low as 200 nanoseconds, which gives us a great resolution. And in addition to that, we also have sampling of digital inputs of 3.5 nanoseconds in order to support simulations of converters that work with high switching frequencies. The design of the simulators is modular, so the time step of the simulation is not a function of the model size. We can just connect new devices to the already existing system and increase the model size. And Typhoon also offers built-in test automation capabilities. And I'll just I'll spend a little bit more time talking about the machine solver, because we're doing a demo in motor drives. So basically, the machine solver is a part of the FPGA processor. It supports multiple machine types, and we'll see that in the Typhoon schematic editor library. We have support for the direct import of JMAG-RT models. The solver runs synchronously with the circuit model, meaning that all the machine models also run at very low time steps as the rest of the circuit. And we have built-in position and speed feedbacks for the machine models that can be sent to the controller. So incremental encoder, output sign, encoder, resolver, and protocol-based interfaces. At the moment, the nonlinear models include only saturation of fluxes as functions of currents, but in the near future, we want to expand this and add support for spatially varying machine models. And I wouldn't spend any more time. I will give the word back to Boris, and then we can start with the demos. Thanks.
Fantastic, Peter. Thank you very much for that. And Ved as well, thank you very much for your presentation previously. I would like to use this time to quickly mention to you all that you can ask questions at any point in time, and that we are really trying to answer them as soon and as fast as we possibly can. So right now, I'm just gonna launch a quick poll to you guys while we wait for a couple more questions, and we will move on into the demo section of the webinar immediately following. So we're gonna let it run for another 30 seconds. So please, if you can fill out the poll, that would be great. And we will be moving right on over to the demos. We will have two demos going, one from bedside from the power assist side, and then following that, Peter will be demoing from the Typhoon side. And I want to remind you to stick around. We will have a questions and answers section at the end of the webinar, as well as would appreciate it if you could fill out the post-webinar survey. Okay, so with that being said, these are the results of the poll. So see a lot of people using ANSYS Maxwell. And I guess that's the perfect introduction to pass the talking stick over to Ved. So Ved, I'm gonna make you the presenter, and if you would like, you can take us into the demo sections.
All right, thank you, Boris. Let me share my screen again. All right, Boris, if you can confirm, you can see my screen?
Yes, we can. Perfect.
All right. Thank you, Boris, again, and thank you, Peter, for the presentation. Now we are going to look at the demonstration of what we were actually setting up the framework initially. So first thing, as we all know, is to look at JMAG-RT. How do we create this high fidelity lookup table? So as we have seen some of the steps initially, we will just follow the same flow chart and try to generate an RTT file and pass it on to Peter, who will show us further how he will integrate that to Typhoon. So here we see the first and foremost thing is for us to create an FEM model. So for that, as I said, there are 4 ways of doing it. First thing is either you can do it by JMAG Express or JMAG Designer or measurements, or you can also download the model from Motor Model Library. So today we'll see the case where we are actually creating an FEM model in JMAG Designer and then we will create an RT file from there. So I will switch from my presentation to JMAG. So first of all, quickly looking at the website, jmaginternational.com, you do have, if you go to technical library and application catalog, you do have a bunch of examples on there for any of your EM design or any of the motor models that can be downloaded. Provided you have a trial license, you can also download, open it on your end and test it for yourself. And if you want to learn more about JMAG-RT as well, on our website under products, you can go and look at JMAG-RT. And it will also give you access to the motor model libraries where you can download and also look at different examples on there. All right, so the first way of creating JMAG-RT, as I said, is a template-based tool, using a template-based tool, which is JMAG Express. So JMAG Express is basically this template-based tools. You can see there are a bunch of templates of different motor models. You can pick and choose any design from the commonly used templates on here, or you can also build a combination of your own rotor and stator model by picking up from most commonly used designs there. All right, this is one way. And then once I pick and choose any of the motor model, what happens is it will give me an opportunity to put in the parameters required, either by requirements of the, if I know my requirements, it could be rated power, rated torque, or speed and max current and things like that. Or if I know detailed dimensions, material data, winding, and drive conditions of the particular motor, I can also do that as well. And then once I have this, there is a tab where you can directly click on it to create JMAG-RT model. This is one of the way. So basically the first step is to create your FEA model, which you can do it by Express. Or the other way is, today we are going to look at is by using JMAG Designer, which is a full-fledged FEA tool. Now, in this, as you can see there, I have 2D model here, and then I do have my study created with all the parameters which are set up. So I define my materials, I define my conditions for this. Now, under this conditions, I also have loss setting. Basically, I am trying to take iron losses into account as well while I create my RT file. That is the reason I also have the loss condition set up. And then I also mesh the model. Here we go. I can quickly show you the meshing. And then further, the way I can do it is I need to input this into JMAG RT. So for that, I will go ahead and open RT library. This is called as library manager, wherein I can quickly go and create new, click on new, and I can pretty much input different types of machine models, either a PMSM or a stepper motor, solenoids, induction machines, or if you are working with multi-phase machines, you can also use a generic model as well. So as a demonstration for today, we are going to go over creating a three-phase PMSM. Once I click OK, what it will do is it will open up a window where I can select the fidelity that I want to be generating. So basically there are two types. One is an LDLQ model and the other one is spatial harmonics. So when I say LDLQ model, the D and Q axis inductances are dependent on current and phase angle, and the effects of slot harmonics is not accounted for due to the sinusoidal component of the EMF in this particular fidelity. And in spatial harmonics model, this is more accurate model because the model has, the inductances and torque are dependent on current and phase angle, and slot harmonics are accounted for, and the inductance can be obtained highly accurately even if the model has very high magnet saturation, for example. So this can be done. And the third option here where you see use user data is basically when you have the measurement data, you can pretty much input a CSV file of the measurement data here. So typically I can show you the example of a CSV file and the data that can be imported into generating an RTT file from the measurement data. All right, now let us go ahead and for the demonstration purposes, I can select both fidelities, and then I need to input my JCF file, which is the FEM model. So I already saved a JCF file from the FEM model I created. So I will just input that and click OK. Now, once I click OK, it opens up a tab, a window for me where I can scroll through multiple tabs for the settings. So here I will go ahead and open already. I have an example, so I'll just walk you through that. So the first tab is the information tab. Basically, you can input basic information, and then you can also look at the version, model type, and what kind of fidelity you have selected. Pretty much, motor information, if you want to put some comment in there, and if you also want to put the resolution you're using to generate this RTT file, all of this, when you are transferring this RT file to your control designer, or for that matter, anybody, you can pick and choose what data you want to publish or what data you want to share. If you want your motor design parameters to be are something that cannot be shared, you can just uncheck publish so that the data is safe on your end. But in case you are more than willing to share the details, you can click on publish so that when the when the end file is created, when the lookup table is created, you can also see the information of the motor in that file as well. Now, the most important tab is the create tab, where we specifically define the resolution and different components to generate the RTT file. So here, the first one shows me the what kind of fidelity I've chosen, since I've chosen both LD, LQ, and spatial harmonics. And here I define what is the number of poles I can define here. Of course, the configuration of the phases, UVW. Here I define number of turns, which is for this example 35. The resistance I can define. This is the phase resistance. Of course, the leakage inductance as well. Now, moving on to the next one, where it says drive type or undercurrent harmonic. So the drive type, if it is driven by a sinusoidal wave, the option checked here is sine wave drive. Or if it is driven by other waveforms like square wave, you can check the other option. And here is where we define the settings for the current and phase angle. Basically, the number of operating points can be defined here. Now, you can also use the auto setting. Basically, what auto setting does is it creates the data points that are set automatically. You can just enter the rated current, and once you enter the rated current, what JMAG does is it automatically takes the it creates 7 points, basically taking into account the rated current, and it will extend it to 3 times the rated current. Perfect. Now, the whole idea here is to define your operating points, whether the basically current and amplitude. You can go ahead and create a point sequence, or you can manually input your operating points as well for both current and current phase angle. And you can check if you want the same kind of resolution for your torque calculation as well. You can check this. This will, disable this. It will just use the same kind of resolution on for both inductance and torque calculation. In case you want to use a different resolution, you can uncheck and you can define your point sequence as well. All right. Moving on. In terms of LDLQ calculation, again, you can either go by simple settings, which where you define your rated current, and JMAG automatically defines multiple points, or you can click on advanced settings and you can define your current and phase angle. Here, I kind of matched both the inductance calculation and the LDLQ calculation to have the same operating points. All right, and based on the operating points, mix and match, there is number of cases that are defined. The number of compute calculations that will be run to generate the lookup table are shown here. Now, a couple of other things is when you are taking, if your model is taking into account the iron losses, you can always use this tab wherein you can define, hey, how do I want to calculate my iron losses? Again, simple settings. Or I want to choose a point sequence, I just use 2 speeds, and then further, since there are many calculations, you do have the options of basically parallelizing the calculations, provided you have the multi-core running capability. There are different licensing structures that you can use to basically move the simulation faster. Okay, some of the other things is you can also define your mechanical angle resolution here. So by default it is set to 30, but obviously you will define it based on your model and based on the fineness of the resolution you would need. And whenever there is when angle dependency for inductance in each phase has periodicity, in that case, you can use this half electric angle periodicity. Basically, what it does is, again, the calculation time for generating the RT model will reduce based if there is periodicity, and you can set the option to use periodicity. All right, so these are some of the settings which we typically do, and then in case you want to introduce some correction factors, you can do it here. But at this point, I think it's not that important or for this demonstration, but there is an option to also include the correction factors as well. All right, once we do this, we just click OK, and then we check the model, and then we have an option to create model. So we can click on create model, and it starts to calculate and generate the RTT file for us. So I did already have generated that model. So I do have my RT file which I already created. So this is the RTT file. Now, how do I see what this RT file generates, or how do I kind of verify if what my expectation is correct? What if this RTT file is generating according to what I am expecting or what my inputs are? So I have something called as JMAG-RT viewer. This is the tool. So basically, I can go here and drag and drop, or I can just open the file which I just created, the RTT file. I can just call this, and once I open the file, the information which has been published in the while I was creating the RT is pretty much shown here. Whatever is the information I was able to share. So I have all my operating points or data and other information that I share that is available for me here. Now, once I click on more, what happens is it opens up this this additional window, extends this window basically where I can input my inverter ratings and quickly look at some of the basic control methodologies I can use and look at, hey, how is my efficiency map or speed torque curve looking? So once I click on that, I can just quickly view of, I can have a view of efficiency map. Here I'm showing both the motoring and generating modes. So I can quickly take a look at the efficiency maps here. Now, this is a little bit extension of what I wanted to talk, but the idea for here is once I create this lookup table, the RTT file, I will then transfer this over to, or I just pass it on to Typhoon Hill. And at this point, I will pass it over to my colleague, Peter, who will show you how smoothly he can integrate this in the workflow in the HIL of Typhoon Hill bench, and then he will show you further how we can analyze using Typhoon. With that, over to Peter.
Okay, Ved, thank you very much. Let me just continue from here. So, Boris, please let me know. Do you see the Typhoon main window?
Yep, seeing everything.
Okay, good. So today I'm just going to show a short demo of a permanent magnet synchronous machine motor drive in Typhoon Hill. And for that, we're going to be using these first two tools, so the schematic editor and the Hill SCADA. So I'll open the schematic editor, and I have the model that I'm going to simulate already prepared. I'll just go quickly through to give you an overview of how this works and what it looks like. So here on the left, we have a library of components that we can drag and drop, and then connect together to form a system that we want to simulate. So for example, for a motor drive with the JMAG machine, I want to have an inverter connected to a machine, and on this DC link side, maybe I'll have a battery or a source or anything. So the components then, by double clicking on them, you can set the properties. For example, for the inverters, you can designate which digital input pins are going to control which of the switches. You can import losses, you can enable turn on and turn off delays and similar. For basically all of the other components, it's a similar story. So for example, the permanent magnet synchronous machine that imports the JMAG-RT files basically expects an RTT file. You just provided a path, provide the component a path to the RTT file that you want to simulate, and that's it. So then once you've made your system, you can just compile and simulate it. So for today, I'll just quickly go through the specifics of what we have prepared. And it's a simple motor drive. So we have a fixed voltage source in the DC link, a 2-level inverter, and PMSM. In addition to that, we have these two blocks that are going to be used to simulate faults. So one contactor is going to be used to simulate phase A loss, and the other one is going to simulate a short circuit between phases B and C at the motor terminals across small impedance. This, what you see here, so the components in black are basically simulated on the FPGA. So that is our power stage. So the voltage source, the inverter, the machine, and these contactors here, the measurements and the contactors here that simulate the losses. The inverter is switching at 10 kilohertz switching frequency, and the control signals, because I'm not using a real controller, actually come from the signal processing parts of the library. And the actual PWM generator is one FPGA module inside the HIL device that generates my PWM signals. In addition to this, I have the real-time calculation of switching and conduction losses and some thermal properties of the switching modules enabled to simulate. These properties of the switches are imported through XML files that contain all the relevant data. So the thermal characteristics and the losses characteristics of the switches and the diodes. And these files are typically available on semiconductor manufacturer websites. So in case you have a specific switch and you have its design data, you can just, given in an XML format, you can just import it into Typhoon. And I have two of these prepared. So once you've imported them, you will have these properties below filled, and you can do some modifications if necessary. Similarly, the thermal properties of the switches are simulated with these characteristics. And then on the outside,